Once we get up on orbit, we have to configure our rocket ship to fly like a spaceship and be on orbit. So one of the first things we do is open our payload bay doors, and here you see it about twice normal speed on the opening sequence. The payload bay doors have radiators on the inside of them that reject heat from the electronics and the shuttle systems into space. In the payload bay, you see the TDRS satellite with its two antennas folded up umbrella-like fashion, as well as the hexagonal feature there of the solar arrays. In the foreground, on either side of the sills of the payload bay, you see the DXS sensors that we used later on in the flight after deploy. We put those to work starting at about
And we took many pictures of Earth observation sites around the planet. The next scene I think you'll see is a nighttime view, and you see some thunderstorms, some lightning, and in the upper atmosphere of the Earth and some of the cities down below on the left side of the screen. The next scene shows our launch site at night. The city of Orlando, Florida, in the lower right-hand corner of the screen is coming into view, and right about now you can see the Cape Canaveral site, the Cape Kennedy site where we launched about a week and a half earlier, and we intend to land there the next day. In preparation for the entry and the landing, we check out the flight control surfaces and all of the equipment, the computers and such that we need for the entry. And if you think ascent is exciting, the entry is...
I saw from my seat with camcorder recording both over my head up at the upper window, and what you see there is the plasma ionization on entry. And you can also tell by looking at the windows around the John and Don, around the front there, the plasma glow that you've so often heard us talk about. I think the camcorder did a pretty good job of picking up on that orange glow that we see.
Here we have our pilot, Kurt Brown, and looking out the window to his right, you can see the orange glow that's beginning to increase. And this is an overhead view through an overhead window, and you can see the light show that's going on, sometimes rather spectacular as arcing takes place in the plasma above you. We're now getting back into gravity. As you can see, John is holding this cue card up, and it's about a half a G.
In this shot, we've slowed down from our orbital speed of 17,500 miles an hour to about 300 miles an hour, and I'm hand flying the orbiter around the heading alignment circle at about 4 to 5 miles above the shuttle landing facility. It's always amazing to me that this vehicle, which has been our on-orbit laboratory and spaceship, now is configured and comes down and lands like an airplane, with, of course, one big exception: there are no engines running. So we're a high-speed glider, but very, very versatile spacecraft, and of course the only one in the world that can come back and land on a prepared runway.
One of our favorite things on orbit, and this video gives you a good feeling for how rapidly a sunset, in this case, occurs. And we'll cut away to, I think, which is a very nice sequence here of you seeing from the elbow camera the sunset as it occurs on the orbiter. And you see that we have the lights on in the orbiter and continue to work through the dark periods of the orbit.
We still had some secondary payloads and science to conduct prior to coming home. You can see we have a yaw rate. This is looking out the aft windows at a nighttime view of the horizon. And you're going to see the rockets, the The primary RCS jets fire as Ken commands the orbiter to stop that yaw rate. And as impressive as it is here, the oohs and ahs coming from the MSs at the aft flight deck looking out the window at this, they were impressed also. Shortly thereafter, it was time to do the flight control system check in order to get ready to come home. Here you see Ken and myself and Jerry also going through that fairly long procedure to make sure that all the APUs, the flight control systems, and the computers are ready to support entry. Here you'll see the hydraulically powered elevons going through one of their test sequences. And shortly thereafter, actually the next day, it was time to come home. As the orbiter re-enters the Earth's atmosphere, we experience temperatures on the outside of up to about 2,800 degrees, and that ionizes the atmosphere and leaves a contrail behind us that any jet would be proud to lay down. Here's a picture of that contrail going back behind us, and I think you could really see it for about 1,000 miles behind us. You can see the glow behind Ken, and here's Jerry demonstrating that, yes, we are starting to re-enter the Earth's gravitational field. Out my window was the most spectacular view. We had to pull our flight track about 600 miles south, so we were banked to the right, and that gave me the prime window real estate. And this is from about 235,000 feet, about 50 miles in altitude, going over the Canadian Cascades and Rockies, and that gives you a real feel for just the sensation of speed that you get at this point in the entry.
Well, Jim was doing a lot more than giving us a travel log across that high-altitude scorching path down across the northern United States. But here, the whole crew on the flight deck, and I know the training team often wondered what we were doing up there in the motion base, and this is how it looked. We were busy monitoring the displays, watching the orbiter, keeping track of all of the systems as we headed down, getting set up for the intercept of the hack. Here, out the right-hand window, you can see some familiar territory, the vehicle assembly building, as we launched.
And it's an interesting feeling to go from 3 Gs, where your body weighs about 800 pounds with the suits, down to 0 pounds as soon as you achieve main engine cutoff. You see the rockets firing outside for attitude control of the vehicle. We had another failure of a jet outside, and I was a little bit depressed at the time, thinking back to my first flight up to Mir on 63, where we had a jet failure and we almost didn't get to rendezvous. This flight also was a flight where there was a high degree of congressional interest because of the risk. There were questions about the Russian Mir space station that had the fire. Previously they had the collision, and here's Mike firing some jets during the rendezvous coming up towards Mir. And then a couple of days before liftoff, the Mir experienced another attitude control computer failure, and so they lost attitude control. So there were a lot of questions that we had to answer prior to liftoff regarding whether or not it was safe to go up to Mir.
During our long flight, looking down, we can see some very delicate linear dunes in western Algeria in the great western sand sea of the Sahara. This is a very early morning view. You can see the delicate sculpting of the dunes by the wind. A little bit farther to the east is a big outcropping of black volcanic rock. It's dark gray because of iron and manganese in the rocks. And the Tifernine dunes that are there on the right side, the thumb-shaped dune field, is red because of the iron in the sand grains reflecting light in a different way. And it's a very beautiful dune field bumping up against the hard rock of the mountains there. Over Central Africa, we saw a lot of burning going on. You can see several smoke plumes emanating from the rainforest area in Central Africa, combined with the grasslands there. And this was one of the hot topics that we were looking for from space. We saw a lot of burning not only here, but also in Australia because it's the dry season there. A beautiful real-time sunset from...
And this shows one of the prints from MC Escher, and if you look at that staircase, you see it's a little confusing about what's up and what's down. The Escher staircase we had in the workstation looked like this, and it turns out that when a rat walks on this maze, they are actually making 3 90-degree turns, but they come back to the same starting point. And this can help understand how their brain is controlling their sense of orientation. This display actually shows nerve cells in the brain firing when they get to certain locations. We also had rats that were learning to walk in space, and you can see this rat here is using its front legs, and this one is just enjoying floating around. And they adapted pretty much the way we did, since we tended to use our arms and float around too when we were out in the space lab. This is a picture of an oyster toadfish, and it turns out that the balance system of fish isn't all that different from that of humans. And by studying nerve impulses from the fish, you can get some insights into how the balance system is working. Here, Kay is giving some accelerations to the aquarium where the toadfish was. We also had crickets on board, 2,000 crickets, and here Scott is looking at these crickets. Some of them are in a centrifuge that you saw spinning around there, and others are floating around in the weightlessness of space. They actually have gravity sensors, and you can see what happens to gravity sensors when they develop in space.
Now this is, I'm at the glove box doing that protein crystal growth there, and I'm actually using a restraint system developed here at JSC called Albert. We refer to this as Albert the Thing, as opposed to Albert the payload specialist. And I'm working on protein crystal growth, and as you know, these crystals are used to help design drugs for diseases. And it's kind of a lock and key sort of effect where if we can grow more perfect crystals, we know what the lock looks like, and the drug is then the key.
Here I am at the glove box again on Albert, so to speak, or Al squared. And we're working in the glove box, and I'm really looking at mixing profiles. It's very important in the zeolite community. Some of the zeolite community don't recognize that, but it is when you bring two reacting liquids together. And on orbit, we have some special problems. This is the bubble generation here. We talk about bubbles, so sometimes we don't want those bubbles. And so now that we have them, what do we do? And what we do with them, and this is the main experiment that I use that information to power up and to generate, is you'll see me rotate this cylinder which has the solutions in them after we mix them. And we rotate it in order to take advantage of centrifugal force and throw the heavier fluids to the outside, the bubbles to the inside, so they make one big bubble, which doesn't have what we call a lot of nucleation sites, and allow us to grow fewer but larger crystals with fewer defects. So that's one of the things that we had learned on USML-1 and confirmed again on SpaceHab. This is called CGF. We're doing electronic crystal growth here, and Kathy's in the glove box, a closed area. Very difficult task to take in and out what we call SACAs, and I help her a little bit once in a while, and the commander's documenting it, so if we make a mistake, everybody knows we made a mistake. But we didn't make any mistakes that we'll admit to. And here I am taking the SACA very carefully down to stow, because as all PIs, including myself, they're a little bit paranoid about shaking and vibrating, so it'd be a terrible thing for one of the PIs to ruin a crystal, so I made sure we didn't do that.
In this shot, I'm interacting with the geophysical fluid flow cell experiment. This experiment, again, simulates convection in planetary atmospheres. In this view, you can think of it as a weather satellite, basically looking at the southern hemisphere of the planet. The pole is at the bottom of the screen, and the equator is at the top, and you can see waves propagating around the equator, and somewhat reminiscent of cold fronts propagating down from the pole. Another fluid experiment was the surface tension-driven convection experiment. We all spent a lot of time on that one as well. Basically, in that experiment, you can heat the top surface of the liquid, and because there's a variation in surface tension with temperature, a fluid flow occurs at the surface and also drags around the interior of the fluid. And this experiment has a lot of importance not only to the film coating industry, but also has impact on crystal growth. In this fluid experiment, we were looking at manipulating a drop using acoustic fields. This experiment also had applications to drug delivery systems, and there's a lot of interest in surfactants. In this particular case, we're rotating a drop until it fissions.
This was one of the experiments that we all fought to do. Get up in the morning, you were always tempted to actually change the payload activity plan so that you'd be the one doing drop physics. Because as you can see, each input that you make to this acoustic chamber actually changes very dramatically what the drop does. And so we have a chamber with speakers on all sides, and we're changing literally the speaker pressure to distort the drop and also to do to maybe spin it around like this. What you're going to see coming up is in just a minute is one particularly interesting experiment that we did where we actually brought two fluids together. This isn't quite it yet, but we used this experiment to learn what happens when we do have two fluids, with what happens when we have a bubble inside a bubble. But when we brought these two fluids together, they actually had an interface in between them, which we refer to as the beach ball. And what this is going to be used for, it was a development model for actually forming vesicles for drug delivery systems. Now, we didn't really develop a drug delivery system, but we did look at the way two fluids would interact in a single chamber. You can see that's what happens when you do the wrong thing with the knob.
We had, as Katie said, 6 channels of video down, and this may be the first space flight or space lab flight ever where video downlink was not the limiting resource in planning. And also, most of the PIs left Marshall at the end of the mission with all of their data, whereas on USML-1 it took 7.5 months to get all their data out to them. So this was the first demonstration of that. It's something that we'll certainly need for space station. And that and the data uplink and downlink we had were kind of the first demonstrations of telescience that I think we've ever done. Another fluids experiment we had on board, which was an awful lot of fun, was the fiber-supported droplet combustion experiment. We put a small drop of a fuel on a fiber, and the only purpose of the fiber was to keep the drop where we wanted it to be, and ignite it. In one camera view, this one, you could just see the drop shrinking as it's being consumed. In another camera view, you can't see much of the color of the flame front, but you can see that the fiber on either side of the drop is being heated, and that's where the flame front is propagating. We learned a lot from doing a drop physics module on how to deploy these drops and get these guys burning. There was a little bit of trouble with this experiment, as anybody who worked a flight here knows. Mike was our IFM person on this and got it working.
We also had another series of theoretical, I'd call them, experiments on crystal growth, and what we were looking at is hard sphere models and how they would represent the formation of a crystal structure and the interface between that crystal structure and the fluid from which it formed. And we also use lasers to look at diffraction patterns to find out exactly where that interface was and what kind of crystal formed. And the crystal structures that were formed were not those that were predicted. They're still analyzing why that is. So that was kind of a surprise.
While the payload crew, the 4 of them were in the lab, the orbiter crew, we had some experiments up in the middeck too that we were working on. We activated and deactivated some protein crystal growth experiments. We also, and I'm from potato country in Colorado, was pretty proud of the fact we managed to grow 5 potatoes in space. And I'll let Mike talk about that.
This is just an example of me giving some CO2 to the plants inside, and the real goal behind the experiment was to determine how to make a nutrient delivery system, both water and other nutrients, to the plants in case we, for long duration missions, we need to know how to grow those foods so that we don't have to take them with us.
This is the bioreactor experiment. It's one of the, I think, most exciting experiments on our flight. What they're trying to do is actually grow three-dimensional body-like tissues outside the human body. It's something that's very difficult to do here on the ground under the influence of gravity. The experiment worked extremely well. They got very large-size tissues. You can see inside the chamber right there. And this was the first flight of this configuration, and the hope here is that one day we might be growing replacement organs and really understand how tissues actually grow.
This is an experiment conducted with the National Institutes of Health, NIHR. We flew 10 pregnant rodents, and we were looking at musculoskeletal development changes in microgravity.
This is an amateur radio experiment called SAREX that we flew on board. We talked to a total of 8 schools, mostly in the United States, but we did talk to one in Argentina. And that was a great thrill for these 8-minute passes to be able to talk and share the excitement of spaceflight with many students around the world.
This is an experiment called the Space Tissue Loss Experiment, looking at the development of Medaka fish embryos. Again, we're looking at embryonic development and microgravity. This is an interior view. This is near the end of the flight. You can actually see the blood flow through the embryo. And actually, they saw quite a significant difference between our downlink video of those developed in microgravity versus the ground-controlled studies. This is one of the cameras that we flew. It's a multispectral imaging camera. It's looking at thruster plumes and also water dumps. This is an example looking out the side hatch of a water dump with a Windex camera. And next you'll see a thruster firing that was filmed out the aft window. We did a series of primary jet thruster firings, and they're looking at the chemistry and physics of the emissions from the shuttle on not only the shuttle but also other orbiting structures.
Another experiment we flew was again using a multispectral camera. And this is called Hercules. It's a pretty big beast. It weighs around 70, 80 pounds, and here on Earth we had to actually rig up a tripod to practice using it at all. But we actually had two of us using it to aim, because it's like looking through a soda straw, and we're looking at targets on the ground, and the big bump on the top of the camera is an inertial measurement unit, and the hope is that we can accurately look at places on the ground and also be able to look at the latitude and longitude. Here you see a picture of Guantanamo Bay, Cuba, and you can see pretty good resolution. It's jumping around there, so real time it's a little bit tough, but it's going 30 frames a second, so post-flight people on the ground can really look at it pretty well. And this is a picture of a city at night. It's totally dark out for us in Australia. So the Hercules has a lot of potential and had a couple of problems in the beginning, but through the hard work of people here on the ground, we got it to work.
And this is an experiment called the Visual Function Tester. As you know, when you take away gravity, some pretty dramatic changes happen in the human body, and one of those changes is that the eyeball shape actually changes and the vision is affected.
This is a picture of Hurricane Chantal, which is forming in the Atlantic. Luckily, it didn't hit land, it turned north, but we got a good view of this on flight day 2 and 3, passed almost directly over top of it.
This is passing over Egypt. You can see the Nile River there in the lower left and coming up on the Red Sea. This is a beautiful pass always, because you have the very light brown soil and the blue water there. And one morning, shortly after our wake-up music, somebody peeked out and said, "Hey, we're going right over Egypt and the Nile River, and you should see us all scrambling, getting up as fast as possible and getting our noses up to the window there." But it's a spectacular pass, and this is one of our great entertainment mechanisms up on orbit, is just to look out the window and watch the world go around.
We were proud of this shot. There was actually 3 planets in this view, and of course you can see something similar to this right before sunrise on Earth. This is Venus and Mars coming up just before sunrise. The advantage we had being in the orbiter was that we could set the cameras up on one rev and an hour and a half later actually take the scene. Happened very quickly, but again we thought it was a spectacular shot and took the time to capture it on 16mm film. You never get tired of looking out the window, as Don's emphasized. And you can see the orbiter tail and OMS pods in the upper right-hand corner.
This is again looking out the window even at night is spectacular. This is over Asia and the Pacific, and you can see the Earth glow, which I'd never really noticed in pictures before, and it's real evident on how tenuous our atmosphere is. And looking at the lightning storms, literally for hundreds and 1,000 miles, you can see the lightning going off, and you can see how it propagates all across the continent, all across the ocean. It's really a